I don't know. Are they allowed? But you need to pay more, right? Or no?
Well, that would be problematic.
Are you paying by number of credit?
It's like 20.
Yeah.
Or over 12 is the same.
Yeah,
Then
so
you
you
should
can
take
take as
it.
many credits.
Get it for free.
Yeah, but can I get a stipend to do that?
Stipend? No, it's
Give me
free,
a
right?
stipend.
And you guys are all very excellent. You are going to get 4.3 anyway, so with 2225, right? Anyway. Okay, so what did we learn last time? This is a plot I want to remind you again that if you have one pole, your maximum phase shift is 90 degrees, right? If you have two poles, you can go to negative 180. You have three, then you have negative 270, right? And we said that why we care about this, because if we assume that we have a feedback system, and we assume the K is real, which is possible because we have so many examples that the K was constructed by using resistor divider, right? Voltage divider, or just simply one resistor. So it has very high bandwidth, right? So purely resistive. So in this case, the pole of this KH determined by H itself, right? Because it is real. And let's assume it is also positive. And here I don't know why I put 1 and no one say it's a mistake, right? When it is positive, right? What I'm saying it is assume it is positive, right? We assume it is positive and also real. So there's a possibility that when you go to a high frequency, the H will change because the H can be one of these. Okay? And if it is one of these, particularly the free poles one, right, you might get into negative 180 degree at finite frequency. And then what happened? There's a possibility that you will have 1 minus 1, right? This is a hand-waving argument. Of course, that's not how you do the stability analysis, right? But we don't go deep. I also don't know this well. But the point is that you obviously can see that when it is negative 1, you are going to have infinite gain. And then that causes the oscillation. And the main point is that because you constructed a negative feedback, and then now you, by relying on the fact that both H and K are positive or negative, doesn't matter, but you construct it so that overall is negative, right? But now the sign of the H got flipped. Then as a result, you have a positive feedback. But to analyze this, we want to look at the Bode plot of KH. Because if I just need to look at the magnitude and also the phase, then I will know that whether it's going to have an oscillation, right? And that's why this is important. The point is this: if we define two frequencies, right? One is gain crossover. It's great that some of you tell me that you studied this in the control class already, right? So it's a good review. Gain crossover means that the gain KH becomes 1. Okay, that is the frequency at which it becomes 1. That is the gain crossover frequency. Before that, it still has a large gain. After that, it has a small gain, right? This is log. That's why 0 dB means it is 1, right? Another frequency is the phase crossover frequency. It is the point at which you have negative 180 degree phase shift. Because we know that from this analysis, if you happen to have a large gain and also negative 180 degree, you are going to oscillate. You are not stable, right? So we hope that before you reach this negative 180, your gain is small enough, right? It's difficult to memorize this relationship, but memorized by the physics, right? I want it to have small gain before that it reach negative 180. Means that before it becomes a positive feedback. Then it's easy to memorize. So in this case, in this particular case, you see that when the phase reach negative 180, the gain is still larger than 1. It means I start having positive feedback when the gain is large. then of course there will be oscillation, right? So you want to gain crossover frequency to be smaller than the phase crossover frequency. But in this case, it is not. On the other hand, in this case, before it reach negative 180, so it's not completely positive feedback yet, my gain already reached 0 dB, which 1, right? So it means when you reach negative 180, I'm small enough. Even you have positive feedback, you are not going to cause oscillation. That's the way I memorize it. Is this okay? Yeah, memorize in this way, right? And then, of course, we say that this is a very important concept, as I mentioned at the beginning, in electrical engineering or any engineering. Everything is continuous. There's no abrupt change. Same for 0 and infinity. 0 just means very small. Infinity means very large. It doesn't mean infinity, right? And same here, you cannot just argue like a kid, right? When we are young, like a kid will argue with our parents. I just do this. I did not step over the line, but I deliberately put a line. Just touch my feet, just touch the line, right? You should not punish me or whatever. Right? We like to play this game. But in engineering, it is not. It's continuous. Do not tell me that you just 0.001 degree away from the phase crossing over frequency. Then you think that you are stable, right? In this case, gain crossing over frequency is at the same point as the phase crossing over frequency, then it oscillates, right? And if you shift a little bit so that the phase crossing over frequency is a little bit larger than gain crossing over frequency, you will oscillate also because your transistor, your circuit is not ideal. It fluctuates at different temperature, right? So you need some phase margin. And you can understand the margin means that I need to shift my gain crossover frequency much lower than the phase crossover. Because if I make the gain small enough earlier, then it won't oscillate, right? But again, how much do I need to shift? If I only shift a little bit, yes, theoretically it won't oscillate, but it may take very long time to stop oscillating. You have this ringing problem when you apply a step function. So it is not a good circuit. It works, it functions, right? It's just like I can get my degree in 100 years. Yes, you can get a degree, but become meaningless 100 years, right? You want to get in 4 years, 5 years, 6 years, right? So here, then we say, let me shift enough, and that is the phase margin. So how do you find the phase margin? It is like finding at the gain crossover frequency what phase shift you have. So this writing is really difficult to read, right? I mean omega gain crossover. So let me make it better. The angle of the H at omega gain crossover. Still difficult to read. Angle of H at omega gain crossover. Okay? And then the difference between this and negative 180 degree is the phase margin. Now you can imagine that if I try to make it really, really small, right? The gain crossover frequency really small, then I will have a lot of margin, right? What is the problem of this? Lower bandwidth. Very good. Your question?
The other question I had is, is there a rule of thumb for approximating a good phase margin, or would we have to evaluate system components every single time?
I think usually people ask for 60 degree for a good system. Yeah. And you actually taking the graduate class, right? I think they gave you a margin. What was that in the project? Do you remember? You don't remember? Okay. Yeah. Definitely more than 45 in a practical case. Yeah. Okay. 60 would be a good one. Yeah. So good, right? So for example, this difference is like 60 degree. Okay. Good. So now what if we have the oscillation problem? Now let's look at the left, right? This is the original design. The gain crossover frequency is here. The phase crossover frequency is here. Is it going to oscillate? It is, right? Because if you look at here, you find that when you reach negative 180 degree, your gain is still larger than 1. Then your system is going to oscillate. Then what can we do? How can we solve this problem? Then you will say, can I do something to push the gain's crossover frequency to the left? Right? If I can push it to the left, then now you see that this point, if you look at this one, is less than 1 for the compensator design. Right? For the original design, it is larger than 1, right? When my phase reached negative 180, the gain was still larger than 1 for the original design. Somehow I did something so that I moved the gain crossover frequency to the left. And then my gain is less than 1 when it reached negative 180. Is that okay? That is the purpose. But is this possible? Can you think about this? Is this possible? Basically, what I'm saying is that now I reduce my gain, but at the same time, I keep the phase unchanged. Can you think about what are the possible? How can I do something to my amplifier so that the gain is reduced, the gain crossover is reduced, but the phase crossover is not changed? Just whatever come up in your mind. Say again? Feedback? Yes, but this already has a feedback. Think about the body ports, right? Think about this. You're basically telling me that add an additional pole. This is a good idea. So he said, for example, make it lower, right? But then what will happen to your phase when you add an additional pole? Yeah, you actually will increase more, right? Because every pole actually reduce another negative 90, right? So you cannot do this by just adding a new pole, because you are going to also increase the phase, reduce the phase crossover frequency, right? So what are the other possibilities? By just looking at this figure, how can I reduce the gain without changing the phase? So he said, move the pole. But if I move the pole, isn't that the phase will also shift to the left? The phase crossover. Yeah, but you are there actually. You are there. But because what I'm challenging you is a single pole system. For a single pole, of course, you remove the pole to the left, then your the gain crossover will move to the left, but the phase crossover will move to the left also, right? But however, there's no oscillation in single pole because it's negative 90 only, right? How about this? Anyone think of other way? How about this? What if I just reduce the DC gain? Do I remove the gain crossover to the left and not changing the phase crossover? Do you agree? This is a possible solution, but my gain is reduced, and that is bad, right? So this is, I just want you to think about that, okay? So what is the solution? We need to first look at this, why we have negative 180. It must come from free poles, right? So let's remember this one. You only can really reach negative 180 if you have free poles. This one is approximation. You only reach negative 180 at infinity, right? So But however, the negative one, first negative 180 is due to the second pole. So this is the scenario. Here I have 3 poles. P1, P2, P3. Is that okay? So I have a DC gain, and then what is the slope here? Negative 20, negative 40, negative 60 dB per decade. Yeah. Now then I look at the shift of the phase. Nothing happened until I reach 1/10 of P1, it start going down. And then after P1, it is at what angle? What is this angle? Say again. Negative 90, right? First pole. Then I come to here, I see my P2. Then it will shift again. And that's what gives me negative 180, right? Even though it is not exactly 180, if I have not seen the P3 yet, it is very close to negative 180. This is not good, okay? And then later I see P3, I have another one. What do I get here? What's the angle? 270. Okay, so what is the problem now? I reach approximately a negative 180 here because I have 3 poles, right? Of course, you can, even if I don't have the third pole, this is also ugly. No, I mean, it's negative 180, very close. It's not going to be, to give me some good signal, and it's very marginal, right? Let's look at the gain at this point. What is the gain in the original design? Maybe I should not use the green, otherwise you think that this is compensator. Let me use red, right? The gain is very large, right? Because the previous gain crossover frequency is here. This was the gain crossover frequency. The gain crossover frequency is larger than the phase crossover frequency, right? And that's why it is here, right? Make sense? So what can I do? What I'm going to do is to add a compensation capacitor. I will show you later. To move P1 to the left. Okay? So this one is like what you said, move it, right? So when I move it, however, what it really moves is only the 90 degree. I move P1 to here, now this becomes negative 20. So it start going down very fast. But I also move the phase shift to the left, as you can see from here, which is negative 90. But we remember that, as we said, compared to the gain, the magnitude, the phase is different in the sense that it saturates after the first pole. It's always negative 90 until you see the second pole, right? So your second pole is still there. It's not moving. Second pole is what giving you negative 180. And by doing this, now my gain crossover frequency is about here. So that my gain crossover frequency is now smaller than the phase crossover frequency. This is omega gx dash. Is this okay? So basically the idea is that I move the first pole, like what you suggested. But earlier when you suggested I only have 1 pole, I just try to trick you. I say that, isn't that you move the pole to the left, both the gain and also the phase will be shifted? It's right. But there is only 1 pole, and there's no oscillation anyway with 1 pole. Here, this is exactly what you suggested. I move this to the left, so I have I move the gain to be smaller. The gain crossover frequency is to the left. Yes, I do move the phase change to the left, but only affect the negative 90 part. The negative 180 parts is due to the second pole, so it doesn't change. And that is a way for us to avoid the oscillation. Any questions? Okay. If no, let's look at a real case, right? What type of amplifier is this? Okay, very good. One say is Cascade, right? And then Cascade. Okay, what is, so the first day is Cascade. And everyone agree? Yeah, because the input is to here, output is here, is a Cascade amplifier. What is this? Current source. Right, it's just the biasing circuit with a constant bias, right? And then what type of circuit is this? Very carefully. Common source. Why it is a common source? Because the input is to the gates of the PMOS, the output is from the drain of the PMOS, right? Don't make mistake anymore, right, for this. Be very careful. Okay, any question? So this is common Cascade followed by common source, right? What is the gain of this circuit? It's going to be really large. What is the gain of a Cascade amplifier? You can do approximation. Say again. You can give approximation. GMR squared. Negative. This is the approximation I'm looking for, right? GMR squared. That's why we did Cascade. Then what is the gain of the next stage? Negative GM 5. I mean, of course, this is a little bit troublesome because we have two M5, M6, M6 as the bias. It would be better if we put it in this way, right? But that's okay. I mean, just in the order of GMRO cube, a very high gain. It's talking about maybe 1,000. That's a lot. 1 millivolt become 1 volt, 1,000. And it's so easy to make it, right? But this circuit is not going to work if you just use it in a feedback, because it's going to oscillate. It has 3 poles easily, right? You can have, if you really solve the circuit, you find that one is the input pole, right? This input pole has the no, does it have Mueller cap? Do you remember if there's Mueller cap? I mean, both answers will be correct, but you need to explain why. So this is like, we don't need to go to this detail, but treat it as a review, right? So you say you have a CGD1. So do you have a Mueller cap for the first pole? If I say I have a RS as the input, what's the input pole? Just if you forgot, right, just follow the rule. Write down all the capacitor. How many capacitors do we have? 4. And then at this node, how many capacitor is associated with this node? 2. What are they? CGS1, right? But then what is the pole of this one? Pole A. What's the pole? Just sum of these two? We should not answer this now. So you are saying this is just 1 over RS CGS1 plus CGD1? You need to just follow all the rule. How come, just step back, right? How come you know it is just RS CGS1 CGD1? How come? How dare you to just say it is RS times this capacitor? Based on what? Why you say that? Based on which method we have learned? But why you did not draw the small signal circuit and find the pole for me? Why you can just say that this is RS times this one plus this one? You are right, but I just want you to tell me why. Because we have learned a method, right? What did we do? What happened in that method? You ground the input and say again. You check the path that take you to ground, and then for resistor, okay, and then resistor is RS. Then what is the capacitor taking you to ground?
Split into
Right. CGD1 does not take you to ground, right? Then we use Mueller, right? So now can you really put CGS1 plus CGD1? Divided by or multiply 1 minus A. Is that okay? I know you know that, but I need to challenge you from this basic, right? Because in the future, you will get lost again and forgot to use the Mueller effect, and which is the most critical part. Because everyone, if they're under constraint and they have not learned anything, they will just guess it's R1 over Rs, which is completely an intellectual guess, right? But you should be aware that, no, I cannot use CGD1 because this is not grounded. I need to use Mueller cap. At least you need to know that I cannot use it. Whether you know how to break it is another thing, right? What is A in this case? I mean, what is the gain? Yeah. What, say again? What is the gain we need to use for the Mueller cap? Minus GM1, RO1. Is that right? It won't be that simple, right? I want everyone to raise their bet. Just ask yourself, what is the meaning of the gain in here? How do you define A in this circuit? What divided by what? Huh? VA over V in. Yes. Then what is VA over V in? Now maybe go back to you. You say that it's negative GM1RO1. Is it correct why you say that this is GM1RO1? Everything needs to be a reason. The reason cannot be because I don't know, so I guess, right? Because you think this is common source. From where to where is common source? From V into A is a common source amplifier for sure, right? Because input is gate, output is drain, right? If I treat this as gain, right? But now the point is, in common source, what is the gain of a common source? Negative GM? Only RO for a common source? RO parallel RD, yeah, and negative. Good. Then where is the RD? No, where? How comes? Then you just draw the circuit, draw the regular common source again, right? Because you want to use that equation, right? This is RO parallel RD. Then where is RD? Here is your A. Where is RD? No. About which one? About A, right? So why is the impedance looking up? 1 over GM2. So this is the whole thing times RO1 parallel 1 over GM2, which is approximately equal to negative GM1 divided by GM2 because RO1 is large. Or if we say we assume no channel length modulation, right? So again, this circuit looks complicated, but that is everything you have learned in this class, right? So why you did not get the answer right? Because you jump into it. Just think about what we have learned step by step, and everything has a reason, right? Okay, so this is the pole. So do we have Mueller effect? Again, both answer is correct, yes or no. Yes is correct, no is correct, but then why? Just say it, and you find that you are the same. Does it have Mueller effect? For CGD1. Yeah, why it has Mueller effect? Because it's not grounded, and in D I'm already using the Mueller capacitance, right? But what is 1 minus A in this case, approximately? Huh? No. A is negative GM1 divided by GM2. 2, right? It's approximately equal to 2. So those say no, also correct because it's small. And as an engineer, that's how we communicate. We say Cascode doesn't have a Mueller effect. No one will say that you're wrong because it's not important. It has a very high pole our way, right? But if it's a common source, maybe this one will come to here because it may be 10x smaller. This may be 10 gigahertz, now become 1 gigahertz. Yeah, so it's up to you. You say no or yes. Don't argue. It's just the magnitude, right? Okay, so this is one of the pole, right? So here, so this is a review. So here now you see that I have a high gain followed by another common source amplifier. That is fine. Before I put something called C compensate, okay, I don't put there. I have this body plot. First it hit B. B has a lower pole, and then it hits the output pole, and then this one. But anyway, the point is that at B, it reduced by negative 90. At out, it reduced by negative 180, and then reduced by negative 270, right? So where is the gain crossover frequency? On the top, by definition. Thank you. This is the gain crossover, right? Where's the phase crossover frequency? Here, right? Omega px. So is this stable? Now this is stable by itself, but once I put in feedback, it is not. Is it this stable in feedback? No, right? So my goal is to use what we said earlier. I'm going to add a compensation capacitor here. So this is deliberate. This is not CGS, CGD. They are still there, but I deliberately add a capacitor there, a large capacitor. And that is what it will happen. Because I add a capacitor, then I actually move the pole to here. Okay? And then what will you do? It will just keep, I need to draw it in the right way so that, let me move even more, so in case my drawing is not good. Right, so I start from here. And then I'm going to have a parallel line going down. Do you see that? And then when I hit the second one, I will go down faster. Right, this is the second pole. So now my gain crossing over frequency, I move too much, of course it's not necessary, but just good for my drawing. Gain crossing over frequency is here, right? Where's my phase crossover frequency? Is it still here? I need to check. When I move the pole to here, it means that I will start dropping from here. Correct? Because this is the first pole. And then am I still dropping if I keep going? No, right? Because there's the first pole. Until later, I see the second pole. And then third pole, right? And now my gain phase crossover frequency is here, gain crossover frequency here, then it is stable. So what do I sacrifice here? I did not really sacrifice my gain. What did I sacrifice? The bandwidth, yeah. But maybe this is good enough, right? Because this may be at 1 gigahertz, but my application only need 1 megahertz, then just reduce it. But if that actually make my bandwidth smaller, then I need to redesign everything. Otherwise, I just add a compensation capacitor. Then my circuit will be stable. Is that okay? Okay. So that's all I want to teach for this semester. Now I will review assignment 5 and continue to give you hints, right, and review.